In the last session we saw how to use a tree data structure called heap and use it for sorting application. We also quickly saw a divide and conquer strategy called quick sort for sorting a sequence of numbers. So, in the last two sessions we have been studying this problem of sorting a sequence of numbers and have seen a plenty of ways of doing it. We saw to begin with insertion sort, then we looked at merge sort, then we looked at heap sort, and then we looked at quick sort. We also saw that all these algorithms have different worst case complexities and the base case complexities. I have just mentioned here the worst case complexities because usually, as we said, we are going to be interested in the worst case of an algorithm. So, merge sort we saw worst case was n log n, whereas insertion sort was n squared, and we also saw heap sort, it takes n log n time. We also had observed that insertion sort, the best case happen in linear time, whereas in merge and heap even the best case is linear time. We also saw quick sort where the best time is n log n and the worst case is n squared. So, the obvious question is, what is the best algorithm out of this? Or another question is, can we do better than this? Right? For example, we are moving through n log n or n squared. Can we still do better than this, or what is the best that we can do? So, we are going to try to answer these questions, is how much better we can do or what is the best that we can do, and that would answer then out of this merge sort, insertion sort, heap sort, whether any algorithm is the best or not. Obviously, insertion sort is not the best because in the worst case it is quadratic in its order, whereas merge and heap are n log n. Question is, can we do better than n log n? So, the aim of this class is to, or the session is to show that any algorithm which will sort a sequence of n numbers and is going to be based on comparison of elements, we cannot do better than n log n. So, if you look at all the four algorithms that we looked at, insertion, merge, heap and quick, the algorithms were basically based on comparison of elements. All these algorithms, the key computation that was done was we compared elements and decided to decided what order or what should be the correct position. So, the basis of our algorithm was comparison of elements or comparison of numbers. So, the goal of this particular session is to prove or is to show that any algorithm or any solution that is going to be based on comparisons cannot be better than n log n, or n log n is the best that we can do. Let us look at a particular case of n distinct elements. Again, we have been saying distinct elements is just for the convenience. All the results that we do for distinct elements can be extended to a general case where you can have an element repeated in your sequence. Question is, suppose you are given n elements, say 3 elements. How many possible orderings do we have for these 3 elements is the question that needs to be answered if you want to look at the best case. Right? We know that if 3 elements are there, there could be any one of the following 6 possibilities. If I have 3 numbers, I can have them in an order ABC or BAC or the following order. So, if I have 3 elements, you have precisely 6 possible orderings. Now, any one of this is likely to be a input to your sequence, to your algorithm. So, in the best case or your algorithm, therefore, in the worst case we will have to deal with all these 6 possible cases. So, if your algorithm is correct or is going to sort any sequence of arbitrary elements, then it has to take care of this 6 possible orderings of 3 elements. With 3 elements, we can generalize this to n elements. So, if you have n element sequence, there are n possible orderings that are possible, and any sorting procedure, any one of this n possible ordering is a likely outcome. So, if the algorithm is correct, it should be able to handle any one of this possible outcome. And this is the key to the argument that will finally prove the result. So, any comparison based sorting process, we are going to represent it as a tree. So, each node is going to represent a set of possible orderings and a tree edge results of this comparison. So, a decision tree, every node will be a decision and edge is going to be a result of the comparisons. So, if I look at this particular example, you have 3 elements A, B and C, and there are 6 possible orderings we know of these 3 elements, which has been put in this bracket. So, there are 6 possible orderings that are possible. Now, the comparisons that we have will give us the possible cases. So, if in this case, if I look at this, if your A is less than B, in this case if A is less than B, then we have only 3 possibilities, that is B can be between A and C, or B can be bigger than C, or C can be less than A. So, of the 6 possible cases, if A is less than B, we have only 3 possible cases. Similarly, if B is less than A, we have these 3 possible cases, that is C is between B and A, or C is before B, or C is after A. So, those are the 3 cases which are put here. And as we continue the process, as A is less than B, then we can look at whether A is less than C. So, you already compared A and B, now you need to compare A and C, and depending upon whether A and C or C is less than A, you will have another 2 possibilities. If A is less than C, then you have only the first 2 possibilities, that is A is less than B is less than C, or A is less than C is less than B. And finally, you have compared A and B, you have compared A and C, now you have to compare B and C. Based on that, we will give you the exact ordering. So, if I have 3 elements, your decision tree will have 3 factorial leaves, which are precisely the possible outcomes that can be an output, correct. So, if I look at this, this is leaf number 1, this is leaf number 2, this is leaf number 3, this is 4, this is 5 and this is 6. So, I have 6 possible combinations of these 3 elements, and depending upon the input, you are going to follow one of the path in the decision tree. So, if your algorithm is correct, then it should return any one of these 6 possible leaves. So, what does that mean is, if your decision tree, you are going to represent your algorithm as a decision tree, then this decision tree should have n factorial leaves, and your decision tree, as we see in this case, is a binary tree, that it is based on yes or no in terms of the comparisons. If A is less than B, yes, something happens, if it is no, something happens. So, you have a decision tree which is binary, that is every decision has only 2 possible outcomes, yes and no. So, we will just try to abstract these things and the result will follow then. Now, the different sorting algorithms can be represented by these decision trees. So, what you have here is a insertion sort algorithm represented as a decision tree. So, the worst case number of comparisons used by the sorting algorithm is equal to the depth of the deepest leaf. A decision tree to sort n elements must have n factorial leaves. Now, we also know that a binary tree of depth d has precisely 2 power d leaves, correct. So, we are just going to try to now collect all the facts that we have looked about trees and try to put them in a sequence and derive the result. So, what we are saying is a decision tree to sort n elements must have n factorial leaves. So, this is something we have already observed right now, correct. If we had 3 elements, your decision tree for sorting application should have 3 factorial, that is 6 leaves. So, if you have n leaves, you should have n factorial leaves. So, if you have n numbers to be sorted, then the decision tree used for sorting should have n factorial leaves. We also know that if a tree has height h, then it has 2 power h leaves at most, that is at level h you can have 2 power h nodes. Now, if you combine this, we can show that. So, what we want is precisely, and from this equation we see that what we want is your number of leaves n factorial. So, your number of, so you should have precisely at least n factorial leaves. So, what do I know is you should have 2 power d or 2 power h should be at least n factorial, right. So, what we observe is precisely you should have n factorial leaves and maximum possible leaves of height at height h are 2 power h. So, that gives us the inequality that 2 power h has to be bigger than equal to n factorial, or as we have seen here, it just means that your h, correct, this just would mean that h should be bigger than or equal to log of n factorial. This is just taking the logarithmics of the earlier expression that we have written there. 2 power h has to be bigger than log n factorial. So, h has to be bigger than log n factorial. The log here is to the base 2. Now, let us look at log n factorial and see how to have the order notation for log n factorial. So, log n factorial, we know n factorial can be written as n into n minus 1 up to 2. Then we can use the properties of log. We know log of a into b is log a plus log b. Using that equation or using that formula, you can separate this, and then we can show that this is actually bigger than or equal to n by 2 log n by 2, and then this is precisely n log n. This is standard school algebra that we learn about logarithms. So, what we have proved is that log n factorial is bigger than or equal to n log n. That means any sorting algorithm based on comparisons requires at least n log n comparisons. That is represented by a notation called omega notation, right. So, this is the omega notation that is used to show that the number of steps is at least n log n. Now, that proves the fact that you cannot have algorithms which are based on comparison and will require or which can sort in steps less than n log n. So, any comparison based algorithm will at least require n log n steps to sort. So, that proves that you cannot have algorithms better than merge sort and say heap sort. Such algorithms are also called optimal algorithms. Right. So, that is another terminology which is used is, so algorithm is an optimal algorithm if its time complexity matches with the lower bound on any algorithm that is supposed to solve that problem. In this case, the worst case of your heap and merge is n log n, and what we have just proved is you cannot do better than n log n. That means these two algorithms are optimal algorithms. A natural question is, is to ask is, what we are assuming in this all these results is that all our algorithms are based on comparisons. Now, can there be algorithms which are based on something else, and what are the assumptions for them, and what are going to be the running times for them? One more question one more observation that we can make at this point is, all these algorithms that we have been looking at, whether it was merge sort, heap sort, quick or insertion, or the lower bound results, we assume that we have no knowledge about the input sequence, right? So, your input sequence is a completely random input. There is no idea beforehand about your input. We know well in practice, we have been saying this, if we know well in advance a bit more about the problem, probably that knowledge is going to help in solving the problem in a better way. So, that is what we are going to try to look at next is, can an additional knowledge about input help us in doing sorting in time less than n log n. We know if input is random, then we cannot do better than n log n. So, can we do better? That is, can we have a linear time algorithm instead of n log n? And answer is yes, if the input has spatial structure, that is, we know beforehand that our input is going to be of a certain format. If we know that, then we can use this fact to devise an algorithm which is better than the algorithms that we have looked at until now. So, there are many, they are called counting sort, radix sort and bucket sort. What we are going to concentrate is on bucket sort. So, we are going to concentrate on the bucket sort algorithm. Counting sort, radix sort also uses some additional knowledge about the input and uses that fact to have better algorithms. We are going to concentrate more on the bucket sort in this session. So, let us look at what are the assumptions that we need on input for bucket sort algorithm. Yes, so the bucket sort algorithm makes assumption about the data that is being stored. We assume that the n element sequence that we want to sort lies in the range 0 to n minus 1. That means, we know beforehand the range of the elements that we are being sorting. Number of elements can be many. For example, we might want to sort 100 numbers between 0 and say 20. So, it can happen that some numbers are repeated a lot, many times, but we know beforehand that the number, all the elements that we want to sort are less than or equal to some fixed number, and that is, we will see, can be very effectively used in devising a algorithm which will take time lesser than n log n. So, the basic principle is going to be not based on comparisons, but using the indices and making use of a bucket array. So, we will use keys as indices of an array. So, before we exactly look at the procedure, let us try to illustrate and understand this fact. Right. So, suppose we want to sort this sequence of numbers 2, 1, 3, 1, 2. Right. So, I have a sequence 2, 1, 3, 1, 2. Right. So, this is a sequence of 5 elements and we know it is all elements are less than or equal to 3. So, you are using the fact that number of elements is 5 and your n, or they are all between, and n happens to be equal to 3. That is, all numbers are less than or equal to 3. You have 5 numbers less than or equal to 3. So, we will use this fact to devise a efficient algorithm. So, as a first step, we create a bucket which is going to be represented by an array. So, we are going to create a bucket with indices 1, 2, 3. So, bucket is an array of lists. So, a bucket is going to be an array of lists. So, we will create a bucket of size 3, which is exactly the upper bound on the integers that we want to sort. Now, as we do this, we start now scanning the elements. So, the first element that we look at is 2. So, we know 2 and then we actually insert this 2 at location 2. So 2 is going to be inserted in this. Next you look at the next element 1, insert it at bucket location 1. You again have 3 which goes here, and as soon as you have 1 again, you are going to insert this at index 1 in your bucket array at the end of the list, correct. So what we are having is a bucket of size n. At bucket of size n, at every index I, you have a initially a empty list. So to begin with, we'll have precisely a bucket like this with empty lists, correct. So initially these are all going to be empty. That's the initial assumption. So we'll have 3 buckets. Initially each bucket is going to be empty. Now we start scanning element. You look at the key of the element, you are going to insert it into a bucket at that particular location at the end of the list. So after doing all this insertion, you get precisely this configuration, that is in bucket at location 1 we have 2 1s inserted, at location 2 you have 2 2s and then a single 3. So this is what happens after this insertion into this bucket. Once this bucket is formed with this insertion, we simply pull back the elements from the bucket and put them in an array. Once you have this bucket structure ready, what we do is simply now start removing elements one by one from this bucket and storing them in an array. Once we do that, the array will have only the sorted list of elements. Now we pull the elements from the buckets into an array and we put them listwise. So first we will put up 1 and another 1, then we put up 2, then next 2 and 3. So once at the end of the once we have pulled all the elements from the bucket into an array, what we have is a sorted array, right. So the algorithm basically creates a bucket of size n. Initially at each index in your bucket you have an empty list. As you scan elements, based on the key you are going to insert it into a bucket index at the end of the list. The list that we are going to maintain is going to be a single linked list. We know that in a single linked list, if you are inserting at end, it takes a constant time. So this is what we are going to use to actually write down the complexity of the algorithm. So the pseudocode notation for the algorithm is as follows. So we are going to start with the array of B is a bucket. It is an array of n lists, each of which is initially empty, correct. So if your maximum upper bound is n, you are going to create a bucket of B which is going to be correct. So this is going to have 1 to n, and initially they are all going to have empty lists. So these are all empty lists initially, right. That is the initial part. Now for each item x in S, if k is the key that is represented at x, we are going to insert this into bk at the end of the list. So we are going to remove x from S and insert it at the end of the bucket bk. Once we scan the complete elements, we start pulling them back into an array, right. So once you are already full, for each item x in S, we are going to remove x and insert it at end of the array S, which is going to be a sorted array. So that is a simple bucket sort algorithm. We see that it is going to run in time order of n plus n. You have n elements and n is the size of the bucket, or n is the capital N is the upper bound on the sequence of elements that we have. Easy to see that if n is of order n, then we can sort this in order n time. So bucket sort algorithm is a linear time algorithm if capital N is of order n. And so that means we can, if we have idea about the sequence beforehand, in this case if we know the range of numbers that we are going to deal with, then we can use this effectively and sort the sequence in linear time, unlike other sorting algorithms which we are taking n log n time.